Bismillahirrahmanirrahim. So let's start the second part of the derivation of Schrödinger wave equation. So this is actually the final form of the Schrödinger wave equation, and half of the part we have already discussed in the previous lecture, and you may visit the lecture on YouTube by following this link. So we ended with this equation in the previous lecture. Now I'm going to start the further derivation of this equation, and we will be achieving our final target, which is this. So here, if you have a look on this equation, so one factor is the psi, and psi is also over here, and the second main factor in this equation is the mass of the particle or the electron, and this is the total kinetic energy, this is the potential energy. So right now we have only this psi function, and now I am further modifying this equation to get our desired parameter as mentioned in the Schrödinger wave equation. So the first one is, this is the frequency, and according to our earlier description about this one, velocity will be equal to frequency multiply the wavelength, or you can say v will be equal to mu lambda, or here mu is similar to the c velocity of light, that will be also equal to the mu lambda. And if you get the value of the mu from this equation, so this equation will become like this. So frequency will be equal to velocity over lambda. So I am just replacing the velocity over this equation, and by putting the value of the velocity, this equation will become like this. So what is actually the rearrangement of this equation? When you put the value over here, so this is the velocity in denominator, and the numerator will be the velocity over here. So all these two velocity are going to be cancelled out, and the final form of this equation, after putting the velocity after putting the frequency over here, so this equation will become like this. Now I am further moving to drive this equation, and this is very important part of the Schrödinger wave equation. I am going to apply another factor, that is the differential factor, and it is shown over here, d over dx. So actually, this is the one of the factors in the Schrödinger wave equation. This is the second derivative. So first we will do the first derivative, and then we will move to the second derivative. So after the differentiation of this equation will becomes like this. How it is coming out after the differentiation? Just first have a look a few examples of the differentiation. And here it is the, let's suppose if any of the x variable which you are going to differentiate by using d over dx. D over dx is one of the operator showing the differentiation, and you are going to differentiate x power n, and this is its solution. And what is written over here, the power becomes moved to the first, and this you are going to subtract -1 out of the power, and this is the solution of differentiation x power n. So let's have another look. If this power is 2, so this will be x square, and when you differentiate by using d over dx x square, that would be 2 will become first, because it is the power 2, and you are going to subtract -1 out of 2. 2 minus 1 is 1, so there is no need to write the power 1 over here. It is already understood this is power 1, and this will be coming from the solution, that is solution of, or differentiation of x square will be equal to 2x. let's have another example. If this variable is the exponent form, it is the power of the exponent, then how can we solve this one? And this is also very simple. This is going to be differentiated because only variable over there. So first you have to keep the same exponential power ex, and this is going to be differentiated, and it comes first x, and because here it is power 1, and you are going to subtract minus 1 as we have done before. 1 minus 1 will be equal to 0, x power 0 will be equal to 1, and when you multiply by 1 by this factor, it will remain the same. So the solution of this one, it is the same e power x. So let's have another example. This is very relevant to our derivation. So now you are going to differentiate the sine x. So this is the again the operator d over dx, indicating you are going to differentiate the sine x. So the first is the sine become cos, and this is the x is the maybe the theta or any of the variable. You have to put the same over here. So sine x will be cos x, and this is going to be differentiated as explained earlier over here. So here x power is 1, so you are going to subtract minus 1 out of 1, 1 minus 1 power 0, and this x power 0 will be equal to 1. 1 multiplied by cos x will remain cos x. Another example very relevant to our derivation. Now you are going to differentiate the cos x. So cos x will become minus sine x, and this x in a similar way you can differentiate like here, and this 1 minus 1 power 0, and this will be whole equal to 1. 1 multiplied by minus sine x will be the minus sine x. So this is the differentiation of the cos x will be equal to minus sin x, or sin x will be equal to cos x. So let's have a look over here. So here a is the constant, 2 pi is the constant, lambda is the constant, only variable is the x. So you are going to uh, just the differentiate the x by using this differential factor d over dx, and that means you are going to differentiate the whole equation, but only x will be differentiated, the rest will be the same. So by looking this example, you have a look. A will remain the same, sin x will become cos x, and this theta is the you can suppose this x will be equal to 2 pi x over lambda. So 2 pi x over lambda will remain the same. So just there is the sine is converted to cos, other will remain the same. And in a similar way you have done over here, you can also differentiate this. Actually this is the whole you will consider as the x, and when you differentiate this one, so 2 pi x 1 minus 1 x, when 1 minus 1 will be equal to 0, x power will be 0 will be equal to 1. So the rest will remain 2 pi lambda, and this is the 2 pi lambda is written over here. So the next is the because our this we have already derived, and now we are going to do the second differentiation because this is required in the derivation of the Schrödinger wave equation, and this is the second sorry, this is the second derivation is of second differentiation of this equation. And now because this is the second differentiation, because it is as shown over here, this is the d square over dx square. So square is indicating that is the differentiation of the first derivative, and that's why it is written over here d square over dx square. So we are again differentiating this whole equation. So the first what are the constant over here? A is the constant, 2 pi lambda is the constant. So I am putting the 2 pi a lambda outside this equation because these are not going to be differentiated as explained before. So the this and this value, and what is left now, cos 2 pi x over lambda is left. So cos, differentiation of cos will be minus sign as explained in the previous example. And now you are going to differentiate this one in a similar way. This is the x power 1 and you are going to subtract minus 1, so x power 1 minus 1 will be equal to 0, x power will be equal to 1, and this factor will be 2 pi over lambda, and this is the differentiation of this equation. So it is a very simple, you have done with the second differentiation, and now this is just the rearrangement of the equation. Here you are just I'm just multiplying this with this equation because all these are going to be multiplied. So 2 multiply 2 is 4, and this minus is I'm taking outside. Pi multiplied by pi is pi square, lambda multiplied by lambda is lambda square, and this is inside of the bracket. And again I am moving minus inside the bracket. So there is no change even because all these factors are going to multiply. Maybe you write minus over here or here, it doesn't matter, and not going to change the equation. So this was our first equation. We have already derived this one. So why I have written over here, because if you have a look on this equation, this is equal to this psi. So I'm going to replace this with the psi. So this is the equation coming out d square psi over dx square from this, and it is the same over here. Actually, this is the just the rearrangement of this equation. I am just putting this psi over here, and rest of the equation will remain the same. Now, after further rearranging the equation, just moving uh, before the equal sign, it will become positive, and what is the rest here, it will be equal to 0. And no, actually we have done another factor, that is the second differentiation. According to the Schrödinger wave equation, we have put this I over here, but the important over here is the mass is missing. This was our the main target in the Schrödinger wave equation. So rest I am doing with the equation to replace the lambda with the mass. So let's see what is the rearrangement of this equation. So it is the de Broglie equation. Actually, he proposed the wave-like properties of the particle. So it is having the inverse relationship between the lambda and the mass of the electron. And this we have also explained in one of the previous lecture. You may go to have detail about the de Broglie equation. So now by taking the square on the both sides, so this equation will becomes like this. So h square m square over v square. So dividing by 1, this equation will becomes like this. Why I have done this one? Because this our first equation which we have already derived in the previous slide. So actually here it is 1 over lambda square. So that's why I have modified this de Broglie equation according to our requirement, that is 1 over lambda square over this. So now you can just replace, or you can put the value of 1 over lambda square in this equation. So this equation will becomes like this. So I'm just putting the value of 1 over lambda square over here. So it will be m square v square over the h square. So again, this we have done with the Schrödinger wave equation. This is required, mass is required, but now it is the velocity of the particle is there. So I am further going to remove this velocity, and we need the total energy and the potential energy inside of this equation. So this is our target. By keeping the target, it will give you an easier way to further move towards the Schrödinger wave equation. So total energy will be equal to the kinetic energy plus the potential energy. And here total energy is represented by E. Kinetic energy, as you know, it is a half mv square. Potential energy is represented by the capital V. And this is again the rearrangement because I need the velocity square. So I'm just moving E to this side, or maybe you can further put more to make it more easier to put the velocity to this side. So this will become minus when you moving to the right hand side. So half mv square will be equal to E minus V, and further it is going to divide it by half, and when you move to the right hand side, it will multiply with the E minus V. So must remember this 2 is going to multiply the both of the E minus V. That's why it is written in bracket. If you do not write, then it will be only multiplying with the E. So when you get the value of V square, and this M will be going to divide by this equation. So this is the value of the V square. So when you put the V square over here, actually you have done with the Schrödinger wave equation and it is solved. So this is the, after substituting the value of the V square is the velocity of the particle or the electron, and this equation finally you uh, will get the Schrödinger wave equation, just replacing the V square over here. So V square will be equal to, this is the 2 multiplied by 4, this will be 8, and M, it is M square divided by M, so 1M is going to cancel out, so 1M is left, and this is the H square is the same, and the rest E minus V, and this is the wave function psi. So just you can just put the value of V square and just cancel out the similar parameter, and then you will get the final version of this equation. So actually you have done with the derivation of the Schrödinger wave equation. This is the final form which we have derived right now, and by rearranging this equation, there is no further derivation, but this is just the rearrangement of this equation, because here the total energy will be equal to sum of the total kinetic energy and the potential energy. So this is the total energy, this is the potential energy, and this whole factor is the kinetic energy, or we simply can say this is the kinetic energy operator. And these are the different operators can used we can use in the quantum mechanics, and these are the one of the postulates of the quantum mechanics as well. So here how you can get this one, and again if you just, it is the rearrangement. If you move to the right hand side, this symbol will become minus, and then because it is going to multiply over here, then you actually, if you going to further rearrange, so it will be multiplying, h square will be multiplying over here, and 8 pi square m square is going to divide, and this is the minus sign. When you move into the right hand side, it will become positive, and this will remain the E psi. So this is just the rearrangement, and you can do the further steps on your notebook. If you have any confusion, then you may contact me. Maybe I will help you in further, but there is no, I think, the difficulty to move this form to this form. Another form of this equation, maybe you can replace the, this is the reduced Planck constant, and it is shown by the h bar, and h bar will be equal to h over 2 pi. So when you take the square, it will become h square over 4 pi square. So here you can replace this one in this factor because here it is h square. So 4 pi square, you can put the value of the h square over here. So 2 is left because 4 multiplied by 2 is the 8. So m is left, and this the whole will remain the same. So again, this is the further rearrangement of this equation. So there is no difference between this equation, or this equation. These are all called the Schrödinger wave equation, and with the simplicity we have just moved from one form to another form. So this is all about the Schrödinger wave equation, and I have solved in two different videos. So see you in one of the next lecture.